So today we will be doing chapter 2, which is polynomials. So finally we give a start to algebra. So what are polynomials? So polynomials are the building blocks of algebra. So they are very important. Basically they are algebraic expressions, which mean that they have some variables which have changing values, and we have some constants or coefficients which have fixed values. Now very important points are here that you need to observe. So number one, these constants or coefficients that we're talking about, they should be real numbers. In chapter 1, we've already discussed what are real numbers. They are your natural numbers, integers, whole numbers, rational numbers and irrational numbers. So be very sure that all the constants involved in your expression are real numbers. Number 2, you look for the exponents of the variable. Okay, so every expression has some variables, right? So you look for the exponent as in the power of that variable, and it has to be a whole number. So exponent of what? The variable should be a whole number. Now, you know what are whole numbers? They start from 0 and they go on like 1, 2, 3 and so on. So let's look at some examples of polynomials. So 4x plus 2. Here 4 and 2 are constants, but are they real numbers? Yes, they are. So the first condition is met. Then what is the variable here? X. What is its exponent? 1. Is 1 a whole number? Yes. That's why we are calling this algebraic expression as a polynomial. Now look at this expression. This is in terms of y, but is it a polynomial? Yes, again it is, because 2, 3, 4 are the constants which are real numbers. Talking about the variable y, it has two exponents. Here it has 2 and here it has 1, both of which are real numbers. Then this case is also representing a polynomial. Here we have the constants 5, 4 and root 2. Root 2 is also a real number because root 2 is actually an irrational number which falls under the category of real numbers only. Then x cube and x is what we are having as variables. So x to the power 3 and x to the power 1. 3 and 1, both of which are whole numbers. So yes, this is also a polynomial. Now let's have a look at expressions which are not polynomials, like 1 upon x minus 1. Here if you see that you are basically getting x minus 1 to the power minus 1, which means x will definitely have a power of minus 1, and minus 1 is not a whole number. Whole numbers start from 0. Looking at this case, now if it would have been x plus root 2, it would have been a polynomial because root 2 is a real number and x is having power 1, which means 1 is a whole number, so it is a polynomial. But since it is root x plus 2, it is not a polynomial. 2 is a real number, no doubt, but root x means x to the power 1 by 2. And what is 1 by 2? Is it a whole number? It is not. So it's not a polynomial. Then here again, we can write this expression as x square plus 2x plus 3 whole to the power minus 1. So definitely, when you expand this, you will definitely get some terms which will be having x to the power minus 1. Minus 1 as an exponent is not a whole number, so it cannot be a polynomial again. Now, how do we denote these polynomials? So we look at the variable and accordingly we write it. So polynomial, so P for polynomial, so we have P over here, then we have parentheses, the round brackets, and inside these round brackets we mention the variable in which the polynomial has been expressed. So in this case, if I give you in variable x, it becomes P of x. So 4x plus 2, it will become P for polynomial, and x, the variable is in terms of x. Then similarly, you tell me, how will we write this polynomial? How do we denote it? It will be P of y. This will be P of x. Now, can you denote these? You do not have to denote these because they are not polynomials. Alright. Now, why are we studying polynomials, by the way? We are studying them because for basic of the things, like for the roads which you travel on, all of them are constructed keeping the knowledge of polynomials in mind. Then we have roller coasters. How do engineers design them? The waves and everything. They're all done by using polynomials. So they are very important, even in marketing, finance, etc. Then we have a very important topic, which is degree of polynomials. Now, degree in algebra refers to the highest power of a variable. So if I give you a polynomial p of x, we just saw it means that it is a polynomial in the variable x. So here we look at the highest power, the exponent, the highest exponent of this variable. So whatever is inside, that will tell you the degree of this polynomial. Now why is this degree important? Because based on the degree, we can have different types of polynomials. We can have linear polynomials, we can have quadratic polynomials, and we can have cubic polynomials. Well, we can have any order of polynomials, but we will try to restrict ourselves to these three types of polynomials. So linear polynomials. Now as soon as you hear the word linear in algebra, please remember it means degree 1. So if degree is equal to 1, then it is linear. Quadratic. Now quadratic comes from the word quadrate, and quadrate means square. So obviously here the degree would be 2. Talking about cubic polynomials, cubic, the word comes from cube. So, raised to the power 3, something of that sort. So here the degree is going to be 3. So we just saw that how degree can help in classifying polynomials into linear, quadratic and cubic. Let's look at some examples now. So this is a polynomial in x. So I can denote this as p of x, and what do we see here? What is the highest power? 1. That makes it a linear polynomial. Here this is a polynomial in terms of y, and the highest power of y is 1. So it has degree 1, linear. Here x minus 2 by 11, degree 1, so it's linear. And for degree 2, here we have again p of x as 2x square plus 3x minus 2 by 5. Now here x has two exponents, 1 and 2. So which exponent is taken as degree? The highest power. Okay, the highest power of x is taken as your degree. So that means the degree is 2, which makes it quadratic. Here y square minus 2, highest power is 2, so quadratic because degree becomes 2. Here we see that we have 2 minus x square plus root 2x. So here x has exponent 1, here it has 2. We look at the highest power 2, that makes it degree 2 and hence a quadratic polynomial. Then here we have some cases of cubic polynomials. So here x has power 3, 2 and 1 respectively. We choose the highest power, which is 3, and that becomes the degree of this polynomial, and that's why we call it a cubic polynomial. Here we have variables having 2 and 3 as the exponents. We choose the highest power 3, cubic. Again x cubed, so cubic. Then how do we get the value of a polynomial? So let's understand that by an example first. So look at this question. What is the value of p of x equal to x square minus 3x minus 4 at x equal to minus 1? So what you do here is you say for x equal to minus 1. Now what you need to do is you just substitute it. So LHS would become p of minus 1. So instead of x, you just substitute minus 1 over here. And here you substitute minus 1 in the RHS. So it becomes minus 1 whole square minus 3 into minus 1 minus 4. Let's open this. Minus 1 whole square is 1. Minus 3 into minus 1 is plus 3, and this is minus 4. So 4 minus 4 is 0. So here we get p of minus 1 as 0. Alright. So if p of x is a polynomial in x, obviously if I am saying p of x, it means a polynomial in the variable x. And if k is any real number, so like in this case, k was minus 1. Is minus 1 a real number? Yes. All integers are real numbers. Then the value obtained by replacing x by k, that is what we did, right? We replaced x by minus 1. In p of x, yes, we replaced it in p of x only. And then we got the value of p of x at x equal to k, and we denoted by p of k. Alright, so here what we did was, we just took x equal to minus 1, we made the substitution, and now we can see that the value of this polynomial p of x at x equal to minus 1 is what? P of minus 1, and that is turning out to be 0. So in general, if you have x equal to k and you substitute it in p of x, then whatever value you are going to get is called p of k. As simple as that, just make a substitution everywhere. Alright. Now let me take one more example. So considering the same polynomial, p of x is equal to x square minus 3x minus 4. So if I take x equal to 1, then what would I get? LHS would become what? P of 1. So So now substituting it on the RHS also, we will get 1 minus 3 minus 4, we get 1 minus 7, which is minus 6. Is it clear? So this is, we are getting two values of polynomials. For the same polynomial, at x equal to minus 1, we get the value 0. And at x equal to 1, for the same polynomial, we are getting the value minus 6. Then we have a very important topic again, 0 of a polynomial. So 0 of a polynomial, what do we mean by this? So like in the previous case, we saw that we have p of x and we took two different values of x, minus 1 and 1 respectively. So that value of x, which gives you the value of the polynomial 0, is what we call the 0 of the polynomial. 0 of the polynomial does not mean p at 0, no. It means that value of x which gives you the value of the polynomial. So I'll call k as a 0 of the polynomial if p of k is equal to 0, as simple as that. So basically we can have values of polynomials at any value of x, but only that value of x would be called a 0 of the polynomial if on substitution gives you the value equal to 0. So here minus 1 is a 0 of the polynomial, but 1 is not a 0 of the polynomial because it does not render you the value 0 but minus 6. Alright, so if p of x is a polynomial in x, k has to be a real number, then p of k is equal to 0. If you get that condition, it means k is a 0 of the polynomial. Okay, so if I give you say 2x plus 3 as p of x. Okay, so tell me if x is equal to 0 is a 0 of the polynomial or not. Then do the same thing for x equal to 1. Okay, so if I do it for p equal to 0, on solving you will get 2 into 0 plus 3, 3. So definitely you get some value, but you're not getting a 0. So this is not a 0 of the polynomial. If I put x equal to 1, what am I getting? 2 into 1 plus 3 as p of 1. This is 2 plus 3, 5. Is it equal to 0? No. Hence 1 is not a 0 of the polynomial. Okay, so the moment you get a 0 over here, you say that it is a 0 of the polynomial. So by now I'm sure you can identify how you're getting a 0 of a polynomial. Okay, so just by solving on substitution, if you get the value of the polynomial 0, you get a 0 of the polynomial as that value of x or not. But now how do we get it? So for a linear polynomial, let's see the process to finding the 0 of a polynomial. So a linear polynomial is the one which has degree 1. So it is of this general form ax plus b. So x is to the power 1 over here and a cannot be 0 in this case. Okay, because then you will get p of x as b, and p of x equal to b is not even a polynomial, no variable is there. So if k is a 0 of p of x, then what can I say? So if k is a 0 of p of x, it means p of k should be equal to 0. And what is p of k? If I simply substitute x as k, it's ak plus b equal to 0. It means ak is equal to minus b. It means k equal to minus b by a. So if k is equal to minus b by a, it is a 0 of my polynomial. Which type of polynomial? It's only applicable to the linear polynomial. Okay, so for a linear polynomial, how do you find out the 0 of that polynomial? You just take a and b. Okay, where b is your constant term, a is the coefficient of x. So you take minus of constant term upon coefficient of x. So let's understand that by an example. So if I give you p of x as x plus 1 and I ask you to find out its 0, what would you do? You will just say k is a 0 of p of x if it's equal to minus b by a, right? And what is b by a over here? B is 1 and a is also 1. So it will be minus 1 by 1, which is equal to minus 1. So using this formula, we get minus 1 as a 0 of this polynomial x plus 1. But how do we know exactly? How do we verify this? You already know how to do that. So if you are given p of x as x plus 1, you say for x equal to minus 1, so it becomes p of minus 1 equal to minus 1 plus 1, which is 0. So definitely if you're getting the value of this polynomial 0, so minus 1 is a 0 of the given polynomial. So you can verify it also, and you can find it also using this formula minus b by a, but only for a linear polynomial. Then let's look at the geometric meaning of the zeros of a polynomial. We've seen that algebraically, but geometrically, how do we make sense of it? That's what we're going to do. So be it geometrically, be it graphically, it means the same thing. So we have to plot some sort of a graph. Now, the trick here is that whatever order of polynomial you're having, whatever degree, be it linear, quadratic, cubic, all you need to do is that whatever plot you are getting, okay, whatever, it could be a curve, it could be like this, it could be like this, it could be a straight line, anything. You just need to see the point or points where your curve intersects the x-axis. I hope you know what intersection means. Intersects means to cut, okay, to cut the x-axis. So intersects x-axis. So you look at that point and you just take the x coordinate of all such points, and they will give you the zeros of your polynomial. Okay, so let's see it for a linear polynomial first. So we saw a linear polynomial can be represented by ax plus b, where a cannot be equal to 0 because then you just get b, which is not a linear polynomial. So if I take this ax plus b equal to y, okay, now so far we've been taking it equal to p of x. We can take it to be equal to y also. It doesn't change the fact that it is a linear polynomial. So for a linear polynomial having degree 1, linear comes from the word line. So always remember, be it a linear polynomial, be it a linear equation, okay, whenever you see the word linear, it means degree 1, and that the geometric representation would be a straight line. Okay, so if I try to plot this linear polynomial by taking some x and y values, then you will get a straight line. Now it is not a line segment whose length is fixed. So you can extend it in both the directions. Okay, that is what these arrows suggest, that it is going on and on infinitely in both the directions. Then ultimately there would be a point where the straight line will intersect the x-axis, touch the x-axis. You look at that point and then look at its x coordinate, and you'll find out for a linear polynomial of the form ax plus b, the x coordinate of such a point would be minus b by a, and minus b by a, this would be a 0 of your polynomial. And we just saw a couple of minutes before that k is equal to minus b by a. Algebraically we saw how we can get the 0 of a linear polynomial, and now we're getting the same result geometrically or graphically as well. Alright, so you look at this point. Now how do we make sense of it? So if my x value is minus b by a, this is my y coordinate. I'm getting y equal to 0. Okay, so for x equal to minus b by a, I'm getting my p of x as 0. Now the moment I get p of x as 0, what does it mean? It means that this value of x is a 0 of the polynomial. Now how did we get this minus b by a? I'll just tell you. Now if you want to find out, okay, for whichever polynomial, that which is the point where the curve would be intersecting the x-axis, what you need to do is you write the equation, which in this case is y equal to ax plus b, and whenever you're going to touch the x-axis, the y coordinate will be 0, right? So to find out the points where the line or the curve is intersecting the x-axis, you have to take y equal to 0, because on the x-axis y is equal to 0. So then you get 0 is equal to ax plus b. You pull this b over there, it becomes minus b. So ax is equal to minus b. Then you bring this a over here, you get x equal to minus b by a. That's how we are getting this. Okay. So here we just got 1 0 for this linear polynomial. Okay. Then let's understand this for quadratic polynomials now. So for a quadratic polynomial, the form is ax square plus bx plus c. Here a cannot be equal to 0, because if a is equal to 0, your quadratic polynomial will become bx plus c. X square term will vanish. And then this is what? This is a linear polynomial. Alright, now for a linear polynomial with degree 1, we saw that how was the graph looking? It was looking like a straight line. But for a quadratic polynomial with degree 2, we will get a parabola. Now parabola is a special class of curves, okay, and this is their general form, y equal to ax square plus bx plus c. Now this parabola does not have a definite shape, okay? It can be like this or it can be like this. Okay, it's sort of like a U-shaped curve, right? So here it's opening downwards. So such a parabola is called a downward parabola. And this curve is opening upwards, so we call it the upward parabola. Okay, so depending on this value of A, we get downward or upward parabola. So here A is greater than 0 and here A is less than 0. So far all good. We've just seen the type of curve which we get for quadratic polynomials. It's called a parabola. It could be upwards or downwards depending on the value of A. Now, how do we make out graphically the zero of a quadratic polynomial? Again, I told you the principle would remain the same, which is look for the points where this curve is going to intersect the x-axis and then take the x-coordinate of all such points and they'll give you the zeros of your polynomial. Okay, so here the curve is y equal to ax square plus bx plus c. Look for the points where it's intersecting x-axis and then look at the x-coordinates and that will be the zero of your polynomial. So when you're considering quadratic polynomials, there are three possibilities. We'll just see them one by one. So there is one possibility that your parabola, the graph, which is a parabola, could be upward or downward. It cuts the x-axis at two distinct points. Distinct means two different points. Okay, so in this case, this curve is opening downwards. So what is this? This is a downward parabola. And in the second plot, we see it's opening upward. So we call this an upward parabola. So look for the points where this curve is intersecting the x-axis. So this is one point and this is another point, A and A dash. So you look at the x-coordinates of such points. So this will be the zero of your given quadratic polynomial. Okay, since you're having 2 points here, okay, on which we can see the intersection is taking place of the curve with the x-axis. So here we get two distinct zeros. Alright, and what are these zeros? The x-coordinates of these points, A and A dash. In upward parabola also we see that at points A and A dash, the curve is meeting the x-axis. Look for the x-coordinates and those will give you again two distinct zeros of the given polynomial, which is of the form ax square plus bx plus c. Let's consider the second case where the graph is cutting the x-axis at exactly one point. Okay, now here it appears to be one point because there are actually 2 points, but they're coinciding with each other. Coinciding in the sense that there is one point and another point is right on top of it. So it's getting covered. So we just see one. So like if I give you this point and on top of it, if I give you another point, you'll only be able to see one point and not two different points. So this is what we see here. Here again, this is what? This is an upward parabola. It opens upwards and this is a downward parabola opening downwards. A quick check. Upward parabola gave me which value of A? Greater than 0, and for downward we had A less than 0. That's just some general knowledge. Okay, so here which are the points where the curve is intersecting your x-axis? A and A. We see only one point, but there are actually 2 points which are coinciding with one another. How do you get the zeros? You look for the x-coordinates of such points and those are the zeros. So here you get 2 zeros, but they are same. In the previous case where there were 2 distinct points where the curve was intersecting the x-axis, we were getting 2 distinct zeros. Here it's only intersecting at one point because actually the 2 points are coinciding. So we get the 2 same zeros. Alright. Then we have the third and the final possibility, which is that the graph does not touch the x-axis at all. Yeah, that is also possible. See here, it's at some distance from the x-axis, but it's not touching it. Same is the case with this downward parabola. So in this case, if there is no intersection with the x-axis, will we have a zero? No. So here we have no zeros. So we have seen 3 possibilities, okay, where you can get 2 distinct zeros, 2 same zeros, or no zeros at all. So let's just summarize that. Alright, so if I'm having a quadratic polynomial and I'm attempting to finding its zeros graphically, then there are 3 possibilities. 2 distinct zeros. When do we get them? When the curve is intersecting the x-axis at 2 different points. Okay, then we can have 2 same zeros where there are 2 coinciding points appearing as only one single point at which the curve is intersecting the x-axis, and when the curve does not touch the x-axis at all, we say that there are no zeros. So there is a generalized statement which I'm about to make now, that the degree of a polynomial which we are having, that will tell you about the number of zeros which you can have for that polynomial. So number of zeros of a polynomial will always be less than equal to the degree of that polynomial. Okay, so a polynomial of degree 2, so if the degree is 2 for a quadratic polynomial, the number of zeros would be less than equal to 2, which means you can have 0, you can have 1, and you can have 2. And that's what exactly we saw, 0 and 2 in these cases, right? So the degree 2, if you are having for a polynomial, so such a polynomial will have at most means less than equal to, maximum, opposite of at least. So at most 2 zeros. Now let's move on to cubic polynomials which were having degree 3. So x cube minus 4x, let's take it equal to y. Now here the graph is not definite, like we knew if it's a linear polynomial it's going to be a straight line. If it's a quadratic polynomial, it has to be a parabola. It could be upward, it could be downward depending on the value of a. But here in cubic polynomials, the shape is not fixed. Now you might be wondering, how did I get this shape? It's no rocket science, trust me. All you need to do is you need to make sort of a chocolate bar, divide it like this into several small boxes, take the two variables x and y, take some value of x, and for that you find the value of y. So for example, if I take x equal to 1, y will become 1 minus 4 into 1, which is minus 1 minus 4, which is minus 3. So for x equal to 1, y is minus 3. So similarly, if you keep on plotting these points, whichever you're going to get by filling in these boxes, and when you get these points, you join them using a pencil, and you have to do that freehand. So you will get a shape like this. Okay, so you'll get the shape by joining the points only, and these points can be obtained by taking some values of x, and for that finding the values of y. But what is of interest to us is finding out the zeros. So again, how do you find the zeros? You look for the points where the curves are going to intersect the x-axis. So this is 1 point, minus 2 comma 0. Then this is another point, 0 comma 0. And this is the third point, 2 comma 0. So there are 3 points, 3 distinct points actually, where your curve is intersecting the x-axis. And those points are minus 2 comma 0, 0 comma 0 and 2 comma 0 respectively. Now what do you do with these points? You look for the x coordinates, minus 2, 0 and 2. So these are the zeros of my cubic polynomial. So zeros of this polynomial x cube minus 4x would be what? Minus 2, 0 and 2. Let's take the case y equal to x cube. So here we get a different graph. So it's totally different from what we got before. That's why I'm telling you, for cubic polynomials, there is no definite shape for the graph, but no need to worry. Just make that chocolate bar of x and y values and just join the points freehand and you'll be able to plot it. You'll get the shape then. Now what we need to look for is the zeros, which we get by looking at the points where the curve is meeting the x-axis. So here there is only one point, that is the origin, 0 comma 0. So what do? We look at the x coordinate of this point, which is 0. So 0 is a 0 of this polynomial. Okay, which polynomial? Cubic polynomial, whose exact equation is y equal to x cube.